Another cubic video. And this one is just the salient characteristics. This video is intended to help people visualize the graph of a cubic quickly and easily. All right, there's four things you need to know. Definitely three. The fourth is helpful for all polynomials. Minus b over 3a, c minus 3ah squared, h plus or minus the square root of minus m over 3a. That's it. If you can master those three, you got yourself the graph of the cubic visualized without a calculator. All right, so here's a particular one that I wanted to make sure that the numbers were not too difficult, so we can do all of it in our heads. All right, but even without that, we certainly can do it without a calculator, get a lot of information. All right, so minus b over 3a, the average of the roots, 18 divided by 6. All right, so we have established that there's a point of inflection and x equals 3. C minus 3ah squared, C, 10, minus 3 times A, 2, times H, which is minus B over 3A, and we're going to square that, times 9, gets us minus 44. So I now know that at this point of inflection, I'm going down at 44 to 1. Now, when I plug 3 in, there's an interesting relationship between the quadratic and the cubic terms. They always are in a 3 to 1 ratio and opposite. So if you find the quadratic term, all you got to do is triple it and change the sign. Right? And we'll prove that here by plugging 3 in. That's 54. When you plug 3 in here, you should get 3 times this and opposite. You verify and see if that's true. And then we got 30 plus 5 over here. And that's going to get us our y value of the point of inflection. So if we double this, minus 108, those are the other two, that's 2/3 of that situation, plus 30, plus 5. I get minus 98, 88, 78, and 5 more, minus 73. So that wasn't too hard. And it came from these two situations that are worth memorizing, worth knowing them. Save you a lot of work when you got start finding the graphs and tangents to point of inflection, standardized test in calculus. Well, we already have it. It's right here in the graphing form. Okay, and then all you have to do is take the A term and write the cubic term, and you got the graphic form for a cubic. I did it in the 90s without calculus, and God for help me. I'm going to have to do it again because I'm forgetting how I did it. But I now know that I have local maxes and mins because of the end behavior, right? End behavior, the graph. And so that x value comes from h plus or minus the square root of minus m over 3a. H is 3. That's the point of inflection, the x value of the point of inflection. We already found the rate of change is minus 44, so I'm going to do the opposite. Positive 44 over 3 times 1 is 3. So this is 3 minus the square root of 22/3. That's close to the square root of 7. And so I'm 3 minus a number a little less than 3. And that's what's going to get me this. And this one is 3 plus a number. 3 plus the square root of 22/3 is going to get me this min, local min. This is going to get me the local max. Okay, and I think with a number like this, I don't know how hard it would be to put it in the graphing form. Certainly putting it in the graphing form would be a whole lot easier because the 3's cancel, right? And so I probably could do that without a calculator, but still be messy. It would be an approximation if I use the square root of 3 equals 1.73, but useful information. So I know I have 3 real roots, right, that are going to show up on a calculator. I probably didn't do a very good job of putting that altitude there. I don't know. But, this is quadratic, very similar to the quadratic formula. Very similar, right? Just a 3 and a 3 instead of a 4 and a 4. Right? And cubic, why is it a 3? Probably because cubics are 3-dimensional. Okay. And, the square root of 4 is 2, and square roots and quadratics are 2-dimensional. So something going on geometrically. All right. And so these are the things you got to remember. You got to remember. Well, we could certainly call this b squared minus 3ac the cubic discriminant you know, if this is positive, it sits inside a square root, so it better be positive or you don't have local maxes and mins, so that's another tool useful. But rate of change at the point of inflection, X value at the point of inflection, and finding the X values of local maxes and mins can be done a whole lot quicker, knowing that information. So let's do a standard textbook problem now. And, you know, I've been playing with this stuff and making mistakes and having to do the videos over and over again. So this is my last try. My brain gets tired after I keep doing this for a while. Been up since, you know, early in the morning, get up real early. And let's see. So that's the graphing form of a cubic, the way it's written right now, the interplay of a cubic term and a linear. You'll notice there's no quadratic term there. And so putting that in graphing form could have been written that way, because that's the graphing form for the cubic. All right, so let's analyze this. And I then want to look at something that I've been pondering and let you do some considerations and see if you can sort something out that I've been thinking about. All right, so what do we have here? We've got h minus b over 3a. Well, minus b is 0, right? So 3 divided by 3. So this thing goes through the origin. That's 0, 0. You can plug a 0 in and see 0, 0. Rate of change, c. Well, that's c, right? Because this could have been written as x cubed plus 0x squared minus 12x plus 0. All right, so the tangent to the point of inflection is actually going right through that point of inflection, or a tangent to the y-intercept. And so I now know that I have local maxes and mins. Okay, and I know that I'm going down at 12 to 1, just without just knowing how to interpret that. I don't even have to look over here. All right, but what's this x value and what's this x value? Well, we can get that now very quickly. H is 0, minus a minus 12 is 12, divided by 3 is 4. And so that's square root of 4 is 2. So this thing has the local max at -2 and a local min at +2. And since those are such nice numbers, let's plug them in. So right here, we plug in -2, -8 plus 24 is 16. So this is going to be -16 because of the symmetry. And that made me start to think a little bit about something that's always kind of bothered me. And that's imaginary numbers over here. And let's look at a quick situation. And I'm going to come back to this in a moment. But let's look at x squared equals 9. All right, let's go back to this. Okay, so intersection of two graphs occur at -3 and +3. But mathematicians had a hard time with y equals -9. When does it intersect there? And I think early mathematicians probably flipped this graph over, right? And set it to equal -9. And then in the 1500s, you know, somebody, you know, I think Descartes might have in the 1600s called that I. Right? But if you imagine the graph flipping over, then it intersects at -3i and +3i. And I think that has significant numerical. It's significantly numerical because it's the same distance, but in another direction. And what's I squared do? I squared -1, well, then when we look at 5i squared, you get -5. You get kind of a flipping going on here. So I don't know, just was curious. So I decided that I'd graph x cubed plus 12x and look at the local max and the local min. You see what we get. You know, first off, you don't get any, right? Because h plus minus the square root of minus m over 3a. Well, 0 is h, right? And the opposite of negative, the opposite of positive 12 is -12. And so we're going to get -4 here, right? Which gives us answers of plus and minus 2i. And what were the answers for the max and min over here? +2 and -2. So something seems to be going on there that, I don't know, just finding interesting. I don't know what else to say. But I'm going to think about it a little bit. You feel free to kind of examine more difficult situations. I'm not going to right now, trying to get a video made. So let's have at it. Let's see if you could pause the video. See how much memory you have on what those expressions are. I think they're worth writing down on a piece of paper and looking at for 4 days in a row for 30 seconds, and I'll bet you'll work with them. but it takes a little bit of effort. All right, so what's minus b over 3a in this case? Minus 6 divided by 3 is -2, so I know at -2, I gotta find the y value that goes with it. So I plug -2 in, that's -8. If I triple that and change the sign, it should be that. If I add those together, it should be that. And -2 times -20 is positive 40 and 7. And so that gets me -16, -31. Did I make a mistake somewhere? Hard to believe that it's possible that I could at this stage. So -2 -8, 24 plus 47. So I'm getting 31. This is where my brain gets tired. So let me do c minus 3a squared and see if I made a mistake here anywhere. C is positive -20, minus 3a is 1, h is squared is 4. So that's going to be minus 32, minus 20, minus 12, minus 32. So I'm going down at 32 to 1. Okay, and you can write to me if I make a mistake here, because I am getting mentally fatigued. All right, so cx plus v, in this case, that's the tangent to the y-intercept. So I know I have local maxes and mins because of the end behavior again. And I know that 7 is here. It's lower than 31, and I'm going down at 20 to 1. So 0 gets me 7. So that seems okay. And let's get the x values of the local maxes and mins right here. And but again, if I make a mistake at this stage, I'm still going to post this, and somebody can write to me, or I'll find it another time. So -2 minus the square root of minus m, and m is minus 32, so positive 32 divided by 3a. 3 times 1 is 3, so -2 minus 32 over 3, and this x value would be -2 plus the square root of 32 over 3. Now I'll do some quick calculus to see if these numbers match up for local max and min over here. So, and if you want to get a little head start on calculus, I encourage you to look at the video geometry to calculus, geometry to algebra to calculus in 20 minutes. All right, and explain some of these concepts. All right, so the derivative 3x squared plus 12x minus 20, that's quadratic. We'll set it to 0 because the slopes at this instant are 0. And this is going to find us our slopes at any instant. For instance, if you plug a 0 in, you get -20. Okay, kind of knew that anyway, right? All right. So 2a, 2 times 3 is 6, so that's correct. B squared 144 is correct. -4 times a times c, this looks good. That gets me -2 plus or minus 384 over 6. And I decided to throw the 6 inside the square root. Well, I did it here. All right, so I guess I'll leave that. All right, and then I wanted to reduce that. I thought that was a quick way to check if this became 32 over 3. And I think we get there over here. All right, so 384 over 36. I could divide by 12. That's what I did here. Divided by 12, right? And 12 goes into this 3 times, gets me 36 with 24. And 12 goes into 24, 32 over 3. So it just validates that, you know, there's quicker ways to do things with the cubic than necessarily looking at from a calculus standpoint. This is more a geometric standpoint. And minus b over 3a, if you look at one of the completing the cube videos, you'll see the geometric process there. All right, I think I hit some salient characteristics. I'm running out of gas. And so I'm just going to hopefully post this, and hopefully that number's right, but I'm not going to check it right now. All right, up and running again. Let's see, I'll stop the video and hope this helps somebody.